all complete and ready for use. 38 calories per square centimeter. £8 pounds per square inch. Operationally, a complete ruin. Although a few items of equipment were salvageable, missile hazard was unquestionably heavy. The 15,000-foot installation, around 1 1/4 pounds pressure. Damage limited to collapse of the above-ground tents. A significant finding of these tests was that considerable protection to personnel and equipment would be afforded by revetting field medical installations. 6 Marine LVTs, landing vehicles tracked, at distances from 800 to 4,500 feet from zero, with pressures reaching 22 psi, 2,400 feet, overpressure 11 pounds. Damage was light on all vehicles. On Shot 10, the same vehicles varied from 1,000 to 3,450 feet from zero, pressures running up to 47 pounds. Shot 10 damage was again unexpectedly heavy as compared with Shot 9, with 1 vehicle destroyed and 3 severely damaged in the precursor region, which on this shot extends out to around a half-mile from ground zero. These tests suggest that normal shock waves from high bursts will damage LVTs only moderately up to 22 psi, while low bursts will do severe damage above 12.5 pounds. Curtain wall panels on a series of concrete test cells, some with window openings, some without. The panels were constructed of various masonry materials such as brick, cinder block, clay tile, and combinations of these materials. Similar variety went into roofs and interior partitions. On Shot 9, 4.5 pounds overpressure does this, 6,700 feet from zero. 7 pounds here, 4,400 feet range. Unreinforced brick stood up fairly well, though cinder block and transite shattered. Walls with 20% window opening showed much greater blast resistance than blank walls, though damage to interior partitions was high. 3 framed structures with windows and skylights containing various types of glass and plastic glazings were set up at 7,600, 12,500, and 20,000 feet from Shot 9. Pressures were 4 psi or lower. A few conclusions that can be drawn now are that 1/4-inch clear plastic shattered least of the material tested. 1/4-inch wire mesh was the largest mesh effective in reducing interior missile hazard. Exterior jalousies were worthless, and explosion hardware has very limited usefulness and may even be disadvantageous. Signal Corps placed radial and transverse pole lines, underground wires, and aluminum towers at different distances to test damage effects and determine time required to restore communication facilities. On Shot 9, pressures of 7 to 9 psi knocked down the transverse pole lines at 3,500 and 4,500 feet, and partially destroyed lines at 5,500 feet in the 5-pound region. However, radial pole lines end-on to the blast were almost undamaged. Similarly, towers at 3,400 and 4,400 feet were knocked down, and the one at 5,400 feet heavily damaged. At 6,400 feet, the top section of this 240-foot tower was made unsafe by 4.5 psi. Shot 10 damage to these installations was much heavier. The blast winds destroyed even the radial pole line to 2,500 feet, with static pressures by which it was undamaged on Shot 9. Air Force, Marine, and Quartermaster POL installations were given extensive testing. The major items were 5 and 55-gallon drum stacks, bulk storage tanks, and various subsidiary items such as can cleaning, metering, filtering, and pumping equipment. In general, Shot 9 damage was light or insignificant. There were minor gasoline fires. Drum and can stacks were scattered slightly in the maximum pressure areas, around 16 psi. 2 collapsible 900-gallon tanks were ruptured by 11 pounds at 2,600 feet. On Shot 10, Results were unexpectedly violent. All stacks disintegrated, with cans and drums thrown hundreds of feet and left flattened or badly crushed. All marine fuel handling equipment was destroyed except one collapsible tank. Almost complete destruction occurred at better than 2,000 feet, at the same pressures that did trivial damage on Shot 9. A study of tactical importance. 145 ponderosa pines set in concrete, approximately 6,400 feet from Shot 9's 0. Instrumentation was thorough. A few major types being pressure gauges at 3 heights, time recording anemometers, pitot-type dynamic pressure detectors, and snubber wire arrangements to measure deflections. Pendulums were substituted for the lollipops of former operations to provide mechanical simulation of tree response. As on many of these projects, camera stations were set up to provide high-speed motion picture coverage of blast effects. Thermal input, 18 calories per square centimeter, resulting in only mild char on tree trunks, since the normal ground litter that will ignite at around 3 calories was lacking. Static pressures around 4 psi. Post-blast survey indicated that approximately 20% of the trees were broken, and the missile hazard from falling trunks and limbs would be substantial. There was scant reduction of static pressure inside the stand, but a 20 to 40% reduction of dynamic or drag pressures. Thermal shielding proved excellent, with negligible penetration beyond the 4th row of trees. 16 items of Army rolling stock were exposed on Shot 10 only. A 45-ton diesel locomotive, 1 riveted and 1 welded steel tank car, 13 boxcars loaded and unloaded of various types, 6,600 feet, 2 pounds overpressure, 4,400 feet, 4 psi, 1 empty boxcar turned over, 1 loaded car damaged, 3,400 feet, 6 psi. Boxcars damaged or overturned, 2,800 feet, 7.5 pounds, 1,850 feet, 9 pounds, 1,500 feet, before being hit by 13 pounds to the inch. And here's the same view afterward. The frame of one of those tank cars was thrown against a building 200 feet away. A tank car body went 1,200 feet. The whys and hows of these excessive damage effects at static pressure levels where no such results were anticipated will require further study, as will the mechanics of precursor development over surfaces less suited to the development of heated ground air than the Nevada desert. While to date these damage effects have been observed in the precursor, it does not follow that attack conditions should be chosen to maximize precursor formation. Such effects may be characteristic of any low burst, without regard to precursor phenomena. Although high bursts are still required for optimum damage on many important targets, the tremendous destructive force of a low burst has brought about an interim restatement of damage criteria for drag-sensitive targets, and was the most important single finding of the military effects tests of Operation Upshot Knothole.